Okay, yeah, so today I'll be going over some of the progress that we made for the game Walkthroughs Overcoming project. And yeah, so this project focuses, so one of the goals is to make Warcraft entertaining so it could be enjoyed like spectator sport. For this figure here, it shows some of the different types of sessions for gaming, web archiving, and sports. And the first row shows sessions where only one user participates. So for sports, this would be like practicing play a sport by yourself. For video games, this would be like playing a single player game like Pac-Man. And then for web archiving, this would be like using a browser extension like WarCreate to archive the current web page that you're viewing. The second row shows sessions where multiple invited users can participate. So for sports, this is like playing a pickup game. For video games, this would be like playing an online multiplayer game like Halo. And then for web archiving, this would be like using a tool like Browser's Cloud that can, where multiple users can work together to create an archive. Then for the third row, it shows sessions where anyone can participate. So for sports, this is like watching a professional basketball game on ESPN Plus. For video games, this is like watching a video game live stream, like Twitch Plays Pokemon. And then for web archiving, this would be like watching someone that's live streaming the archiving and replay sessions. And for this project, we've been working on creating gaming live streams and web archiving live streams. The web archiving live streams are competitions between two crawlers where we apply the concept of speedrun to the web archiving process by basically giving two crawlers the same set of CUIs and seeing which one finishes archiving the CUIs first. And we'll give them a higher score for speed, like for that part. And then for the game live streams, we take the web archiving and the replay performance metrics that we measured during the web archiving live stream, and we apply it to the in-game characters. And this is basically just another way to view how well the crawlers performed during the web archiving live stream, just by watching the video game. All right, so now I'll go over the process that we have used or are using for basically the web archiving live stream, game live stream. So first, we create two files. One's a configuration file for the web archiving live stream. Then the second file is just a list of seat URIs. Then at the beginning of the web archiving live stream, we use Selenium to automate basically setting up the browsers and also displaying the context information that's needed for the live stream, like the crawler's name, the current URL being archived, and the progress. So after the browsers are set up, we then give the set of CUIs to the crawlers, and they begin archiving, the web pages. So after the crawlers are finished archiving all the web pages, we then replay all the web pages that were archived and show it beside the live web page so that we can see how well the crawler performed at archiving the web pages. And since we show the viewers the archiving and replay sessions, this adds more transparency to the web archiving process. All right, then after the match is finished, we basically show the results that were measured during the web archiving live stream. We go through each performance metrics that we measured. And then, compute a final score at the end for the crawlers to see which one performed better. All right. And then, so we create like a performance result file that includes all these performance metrics that were measured. And these performance result file is then used for creating the game configuration file. So if a crawler performs well during the web archiving live stream, then the character will have better in-game traits, stats, and abilities, things like that. But if they perform poorly, they'll get worse, character traits and items. Right. Then at the so then we use this game configuration file with either Selenium or Appium So Selenium is for browser games and Appium's for like locally installed games. And these two are just used to automate the interactions with the video game and to, customize the characters and, select which mode we're going to play, like in the game, things like that. All right. And then after all the settings have been selected, the match is started, and then the viewers can watch the match between the computer players. Right. So now I'll go over some of the different demos that we created for the Web Archiving live stream, gaming live stream. Let's first start with the Web Archiving tournament. So this figure here just shows an example of how teams can progress through the tournament bracket. The scores are randomly generated here, just as an example of how it looks. And yeah, so the tournaments that we created so far is a single elimination tournament. So if a team loses once, then they're out of the tournament. But in the future, we'll have other types of tournaments as well, like double elimination tournament and round robin tournament. Okay, and then we have live streamed a WebKind tournament demo like a few months ago, which was between Squidward, Browser, Browsertrix, and WebScriptor. And this image here just shows how it looks at the beginning of the tournament, like showing the tournament bracket, showing Selenium setting up the browsers here, and then the crawler is archiving the first web page. All right. Okay. So then for the Gun Mayhem 2 More Mayhem demo, so this is like a Flash game that's played in a web browser. And yeah, so this was the first game that we integrated with Web Archiving Livestream. So since it was a browser game, we used Selenium to automate the customization of the in-game characters and start a match. And to automate the interactions, we had to simulate mouse clicks, like for selecting the items in the game and sending key presses to the basically HTML canvas associated with the video game. All right. Then for NFL Challenge, this is like an older retro type game, which is like an NFL simulator, and we use DOSBox emulator to play this game. And since that's a local lead install application, we use Appium to automate basically selecting the teams and starting to match for this game. So we didn't use Appium for automating the customization of the in-game players because for this game, it uses text files to change the stats for the players, like for the team. All right. Then we also had a demo. So most of the demos we had before this were just like one match inside of a video game. So then later on, we basically created another demo, which showed a entire season of like 18 games being played in NFL Challenge. So Squidward won the most games here, had the highest ranking. Because for the associated Web Archiving live stream that we had, basically it had the most archive resources, so you got like kind of like the highest score, or like for the overall like type attribute for the players, because most of their attributes was just specific to their one position. But we did use the speed run time to affect the speed of the players. All right. Okay, so for some of the recent work that I've done, I've been working on integrating a third game, which is called Totally Accurate Battle Simulator. So there's two demos I was going to create for this. One is mostly finished, which is a single match demo. But then there's also like a campaign demo I want to create where it automatically creates a campaign during the live stream and create multiple levels. And then for the other work, I've also been working on the same advertisements project, and I've been using the Web Archiving live streams to help with automatically archiving some web pages that have advertisements. So for the Totally Accurate Battle Simulator game, Appium was used to automate the customization of the in-game characters and start the match. And this time, Totally Accurate Simulator is more like it's like a more recent game, and we played this through the Steam store. So this is kind of like an example for like how someone can automate a more modern type game. Yeah. All right, and then for the campaign, which I haven't fully completed yet, but basically for this, we want to like have a campaign that's automatically created that has like multiple levels, and basically each level will be associated with a web page that was archived during the live stream, the web archiving live stream. And for the first example, it'll be like each level will be created based on the number of resources or the types of resources that are on the web page. So there could be like a unit like associated with images, and basically if a web page has more images, they'll have more units of that type of unit. And then we can have different units for other type resources as well, like for videos or I guess if there's embedded web pages, we have separate units for each type. And yeah, and then basically during the game live stream, we'll have like one crawler's team try to complete the entire campaign. All right. Then for the same advertisements project, so one example of like using the web archiving live stream was to see, like checking to see like if an ad that failed to load was archiving or like a replay type of issue. So here, like it shows like a web page being replayed where two ads are not loading successfully. So basically, I would go back to the web archiving live stream and watch the crawling session to see if the ads successfully loaded during crawl time. And yeah, so here it does actually show those two ads like loading in successfully. So from there, since I know how the advertisements now look, like the ad content associated with these ads, I then go through the images in the work file to see if I can find those specific advertisements. And from there, I was able to see that basically the crawler was able to successfully archive, these ads. So basically, in this case, it seemed like it's like a replay, really issue. And yeah, so what we found is that Google advertisements like these two are hard to replay for most replay systems because the URL that's generated isn't correct during replay. So yeah. Okay. So now for future work, for the web archiving live streams, I'm going to apply more gaming concepts to the web archiving live streams, like having a single player mode where it's just like one team archiving web pages, tag team matches where it's multiple crawlers like working together to archive web pages, and an arcade mode, which is kind of like tournament, except it's just like one team that's selected trying to defeat a list of other teams. And okay. And yeah, so for the next future work, I'm going to also identify more motivators that we can try to include inside the web archiving live stream. So like looking at different motivations for like watching live streams and basically like how like some live streams are interactive, try to see how we could apply that to the web archiving live stream. And then also looking at motivators for why people play video games and why people use gamification systems to see what else we could include from there. And okay, and then for the next future work, we're also going to allow like more web archiving tools and web archives to be used during our web archiving live streams. Right, and then for evaluation, we will check like if applying game concepts to the web archiving process, like is that enough to make the live streams entertaining? And then another thing we could do is like to see if there are any like what are the benefits for adding transparency to the archiving process through using live streaming like of the archiving replay sessions. Then for the game live streams, we're going to update them so that they can support more games from different game platforms and game genres. Because so far we mostly be focusing on like competitive games, but there's other types of games that we could try to integrate as well. Some examples like level editing type games. All right. So, summary: we're developing a proof of concept that involves the gamification of the web archiving process and the integration of video games with web archiving. So we have made the web archive process more transparent to viewers by live streaming the web archiving and replay sessions. And we have created automated web archiving and gaming live streams where the web archiving performance was used to determine the capabilities of the characters inside the Gunman 2 More Mayhem, NFL Challenge, and totally accurate simulator video games. Right. Thank you for your time. Okay. Yes, I could take questions now.
Okay, I had a question. So I've been trying to understand this concept since you've been working on it, because it's really cool. But I want to make sure I get it. So you're trying to gamify the web archiving process. That's one of the things that you're doing here, right?
Right.
And so the thing is there like some sort of game that someone would play, and like you and I would sit down and each of us try to compete to figure out, is the goal that one of us gets a better copy of the of a particular seed URL than the other? Or is the goal? Okay.
Yeah, so that is a possibility. Like once we make the live streams more interactive, we could potentially like have competition between the predefined selections that the streamer makes versus the viewers. Basically have like a viewers versus streamer type competition to see which one will do better. That's one possible thing we could do. But yeah, yeah, there could be other possible ways to compete against others with this, I think.
The thing is, I'm building up to something that I think would just like blow this out of the water if it were accomplishable, and that is, if you could reduce archiving to something that's a game, and you have two competitors who are trying to actually archive the page better than the other, and one of them wins or gets a point for it or whatever, you're on your way potentially to a generative adversarial network. And I don't know how you'd structure it or how you put it together, because you know more about this. You're the subject matter expert here. But my point is that that's where my mind went when you were talking about having people compete to complete a task. And I'm just suggesting you might want to at least look at how you might respond to a question about that when describing this work, because right now GANs are a big thing in the machine learning world, and this looks like it's on the way to making an application that you might be able to train something based on. You essentially have two neural networks that compete with each other, and they learn from each other to try to figure out how to archive the page better. You see what I'm saying? It's that this is like another level on top of I mean, you got to do all the work you're doing now before you can even get there. But the point is that this once you've done that, this is primed for the next step to be that. So that's like your future work, or it could be, if you wanted to. For all I know, the problem doesn't lend itself to that, but I'm just throwing that out there.
Thanks, Sean. Oh, I'm sorry. Go ahead, Justin.
No. Please feel free to respond.
No. You're the guest here.
Oh, geez. So I like where Sean's going with this, but I would almost argue that I would almost think that another model to pursue would be one more of collaboration, right? So, I struggled to figure out which metaphor to go with, whether it's, a team full of wizards versus a team full of warriors, or, a team full of, point guards versus centers. But the idea being that it is applicable to the web archiving world. We know that one type of crawler doesn't capture everything because of either speed or quality reasons, right? So could you figure out that okay, yeah. So this is where I think where Sean was going, is that can I figure out that I'm going to need a Heritrix with a a wizard guard complement, or this is actually going to be something suitable for Heritrix to just go plow through. So I think this is a really interesting way of figuring out, is there a teaming approach that we could have for our web archiving tools?
Yeah, and that's kind of what came to mind when I was thinking of tag team matches, like how different crawlers could work together to try to archive a set of web pages. Because some, like are better at archiving, certain types of resources than others.
So just to reiterate what I just put in the chat, there's two perspectives on this project. One is to watch the archiving process as if it is a game where you can watch it on Twitch or YouTube streaming or something like that. So for example, the UK web archive, the British Library, is doing their domain crawl, and every so often they tweet, oh, we're 37% finished or something. There's no way for us to go check in and watch the pages that are being crawled and essentially watch it as a game. The second aspect here is to take the output of the crawling procedure and have it inform or tune a game that people already like to watch, right? Like all the games that Travis was talking about. So those are the two ideas. Now there's obviously more, right? Both a cooperative and a competitive model for the crawlers, but we'd have to figure out a way in which the crawlers could actually learn from the procedure. And that's where I'm not sure it's immediately applicable. There could be something there, but it's not super obvious. But that's my understanding of that.
Well, the thing that I realized while he was talking is that in order to make a game, you have to reduce the problem to something that's a handful of features. And so, well, once you have features, I've been working with a bunch of machine learning people, so that's where my mind went. Once you have features, then you can do something with it like that. So it's just a thought.
Right. Yeah, it's not clear what the features would be, because we either, browser tricks, knows what it knows, and it's not clear how we teach it to know more. Now that doesn't mean it's impossible, but we'd have to have some kind of a scoring mechanism and reflect that back into the code. But the idea of making it a competitive process, cooperative process, is an interesting one as well. All right, so let me see. That's probably it for Travis. Thank you. And next up, I believe we have Gavindya.
So let me share my screen. Can you see my screen?
Yeah, it's better now. Yes.
Okay. So, hello everyone. I'm Gavindya Jayawardena, a PhD student at WSDL and Notes Lab. My advisor is Dr. Sampath Jayawardena, and I will be presenting the project I am currently working on. It is titled RAEMAP. So RAEMAP stands for Real-Time Advanced Eye Movement Analysis Pipeline. So let me start by introducing eye tracking briefly. Eye tracking is a way to measure and analyze eye movements over time so that we can determine where a person is looking at. Eye tracking could provide insight into cognitive behavior of human beings during various tasks, such as visual exploration tasks or cognitively demanding tasks. There are different types of eye gaze matrix that people can generate using the eye movements. One such matrix is fixations. So fixations occur when a person is looking at an area or an object in order to perceive it. One of the major eye gaze matrix is that saccades. Saccades occur when we are changing our gaze from one object to another. So they are like quick jumps of our eye movements. To derive all those eye movements, eye trackers usually provide us the gaze positions in terms of XY coordinates in 2D planes. In this figure, in the slide, you can see there's a participant wearing an eye tracker looking at another person in his field of view. So this field of view in eye tracking terminology is known as a stimuli, and the gaze positions marked in green color are usually taken by the eye tracker that the person is wearing. So they provide gaze positions in terms of XY coordinates. So in this image, there's a person looking at another person. So in this scenario, the person in the field of view is an area of interest that is marked in red color box. So now that we talked about basics of eye tracking and some of its concepts, let's move into how to analyze these eye movement data. So usually the eye movement data is combined with complex analysis software in order to gain insight into human behavior. Those softwares are often capable of advanced functionalities such as scan path generation, fixation mapping, or areas of interest analysis, or heat map generation. Most of the existing software, eye tracking software, are hardware specific and provided with an eye tracking device. Some such examples are Tobii ProLab, SR Research, DataWeaver, People Labs, SMIB Gaze, iMotions. However, these software are often proprietary and must be purchased in order to access advanced functionalities that I mentioned earlier. So this brings us to the question, are there any open source eye movement analysis tools? So talking about open source eye movement analysis tools, PyGaze, Eye Tracking R, EMA Toolbox, Ogama, PyTrack, and Gaze Analytics Pipeline are some openly available eye tracking tools. The problem with most of them is that they are designed for offline batch processing of eye movement data, and they are not designed to process the real-time eye movement data that are being streamed by an eye tracker. So for instance, PyTrack and Gaze Analytics Pipeline, they provide an end-to-end open source solution for analysis and visualization of eye tracking data. However, they both are intended to use after the data collection process, where all the eye movement data is available. So their calculations are done in an offline manner. Therefore, they cannot be used with stream processing, nor with the real-time eye tracking without huge modifications. Also, most of the eye movement analysis tools, they do not support advanced measures such as visual search behavior measurements or cognitive load measurements. So if you're looking to perform such eye movement analysis without proprietary software, one way to go is with the Gaze Analytics Pipeline, because it seems to provide vast majority of the functionalities that are helpful for eye tracking researchers. Let's talk about the Gaze Analytics Pipeline in detail. So the Gaze Analytics Pipeline is an open source software which is capable of processing the recorded raw eye tracking data exported by the eye tracker. Even though I mentioned that it's an open source software, keep in mind you have to contact the author of the Gaze Analytics Pipeline in order to get the code to process, to get this software up and running. It's not available in GitHub or anywhere else. So once you acquire the code, it will provide you with the capability of generating advanced gaze matrix and performing statistical testing on generated measures. The current implementation of the Gaze Analytics Pipeline handles eye tracking data sequential. So in this figure, in this slide, you can see the sequential processing steps of the case analytics pipeline. First, it passes the exported eye tracking data files and extract each trial's data into its own file. So the dir steps and the row steps are corresponding steps for that functionality. Then it filters the row gaze data to classify them as fixations and saccades. So the process step is what takes care of this classification process. After that, the gaze analytics pipeline processes those data files for subsequent statistical analysis. Since the gaze analytics pipeline utilizes split and merge approach, there is a huge number of data files, intermediate data files generated along the way of processing this eye movement data. Therefore, this process is computationally expensive. Additionally, the calculations of advanced case matrix provided in this case analytics pipeline are calculated with the entirety of data available. Therefore, the algorithms designed to calculate those advanced case measures are considered inappropriate for real-time use. So instead of batch processing to generate case matrix, can we build stream-based eye movement analysis pipeline for real-time applications? So to do that, we propose modifications to the gaze analytics pipeline to support stream-based eye movement analysis. So based on the implementation, we propose modifications with the stream processing, and from here onwards, this modified pipeline, we call it as RAEMAP. So the current implementation of the gaze analytics pipeline, as I mentioned earlier, reads eye tracking data that are being exported from eye trackers from the files. Then it does the batch processing to generate those eye movement matrix. In the meantime, it will be generating a huge number of intermediate files. So the modification we offer for this pipeline is that instead of data files, we configure this to read and write eye movement data from and to data streams, so that we can process eye movement data streams as they are being listened and generate those case matrix that gaze analytics pipeline provides, and then output the output generated from those algorithms as output streams. So the main components we introduce here will be the stream reader, stream processor, and stream generator. To simulate real-time streaming of eye movement data during the process of generating those advanced eye movement algorithms to perform in real time, we will be utilizing Streaming Hub. So Streaming Hub has the capability to read data from original file into memory and then generate data streams according to the metadata. So this will stipulate streaming, stipulate real-time streaming with previously recorded data. So in addition, since advanced eye movement calculations provided in the gaze analytics pipeline are considered inappropriate for real-time, we will redesign them for real-time computation. So in this slide, you can see the proposed system architecture for RAEMAP. The base implementation of RAEMAP includes the components from the gaze analytics pipeline. RAEMAP will have a stream reader that is capable of processing the input streams of eye movement data. Then the RAEMAP API will map the input streams into corresponding stream processors. Stream processors will invoke different analytic and visualization modules to calculate eye gaze matrix and then visualize the scan parts. Analytic and visualization modules contain the algorithms to compute all eye movement measures. Finally, the calculated eye movement matrix will output the streams as they are being generated by RAEMAP. So the analytics module in the RAEMAP contains the algorithms to compute the basic as well as advanced eye movement measures in real time. So the basic eye movement measures, as you can see on the left-hand side of the screen, include fixational, saccadic, and pupillary measures. Fixation count, fixation duration are two fixational eye movements we will be calculating in RAEMAP, along with saccadic eye movement measures. Saccadic eye movement measures include amplitude, velocity, and the duration. RAEMAP will also generate pupil diameter, the most primitive metric used in pupillometry, as well as an average of the two left and right pupil diameters. In addition to the basic measurements, RAEMAP will also generate advanced measurements, including pupillary measures and visual search measures. So one such advanced measure is low-high index of pupillary activity. It is known as LHIPA, and it is a measure of cognitive load. It is calculated using pupil diameter oscillations, reflecting moment-to-moment pupil diameter changes. Another advanced eye movement measure provided in RAEMAP is the coefficient K, and that is a dynamic indicator of fluctuation of visual search behavior, to say whether it's ambient visual search behavior or focal search behavior. Another advanced eye movement metric is gaze transition entropy. So this measure indicates the predictability of AOI transitions and overall distribution of the eye movements over a stimuli. So in addition, RAEMAP will also generate the visualizations. So the visualizations module in the RAEMAP contains visualizations computed from the eye movement measures. These visualizations include scan paths, fixations over time, and fixation on AOIs. So one example visualization of scan path is shown in the left upper side corner of this slide. In addition, the visualizations module in RAEMAP is also capable of generating real-time LHIPA. This GIF indicates a snap of how the real-time LHIPA changes over time. And I've also included an example gaze transition matrix that RAEMAP can generate. So this brings us to the end of the presentation. So in summary, in this presentation, I talked about the RAEMAP. It is a stream-based software, stream-based analysis software, which supports generation of eye movements matrix in real time. It is also capable of generating visualizations for those calculated eye movement matrix. I would like to acknowledge my PhD advisor, Dr. Sampath Jayawardena, Gaze Analytics Pipeline developer, Dr. Andrew Dashowski, my project collaborators, Dr. Ann Perotti, Yash Jayawardena, Bhanuka Mahana, SSE, and all the Nerds Lab and Mr. Research Group members. Thank you very much for your continuous support, and thank you very much for listening to the presentation.
All right, great. Thank you, Gavindya. Questions for her?
I have a brief question, just something that you might want to mention. In order to do this, I assume that there are certain metrics that you're just not recording, certain values that is this like a dimensionality reduction problem?
This is more like a generating different kinds of insights given XY coordinates and pupillometry information that we can take from the eye trackers. It's rather dimensionality reduction, yes, but giving different kind of information rather than just the place that the person is looking at in front of them.
Oh, okay. I see what you're saying. Okay, interesting.
Hope that answered your question.
Well, yeah, partially. I mean, this is not my area, but I was curious. If you could go back to see your slide 9.
Okay, this one.
I was very curious as to just like I said, because this is not my area. What does the visualization on the right represent?
So the visualization on the right is a visualization of real-time LHIPA. LHIPA stands for in here, low high index of pupillary activity. So the low high index of pupillary activity is a measurement of cognitive load that is derived using the pupil diameter information that changes from moment to moment. So going back to the visualization, this yellow line shows how the derived LHIPA differs as more information of pupil diameter comes in, whether the cognitive load, like how the changes in pupil diameter happens. The red lines are the thresholds that we use to derive the LHIPA matrix. So what we essentially do is that we count those spikes that occurs outside of those red lines, and we run it through another equation to get the LHIPA value. So in right here, in small text, it shows how much time passed, how many data points we got, and what is the LHIPA that we derive from those spikes.
So
Why did-
Sean, basically it's the, so your eye, the pupil oscillates. So how that oscillation correspond to this particular measure. So imagine that when you are drunk, right? So your pupil gonna get as bigger as possible, try to absorb as much light. So imagine that you are reading a document that is very complex. You are trying to kind of understand this. So your cognitive load kind of represent in the pupil dilation because you're trying to grab as much information as possible. So now imagine that normally the eye tracking folks generate this pupillometry measure is that we grab all these data points as an offline batch, process it, and try to come up with one of these value. But now imagine the problem that we want to do it in real time. Like say, like you are looking at the screen, right? So let's assume that we want to measure your cognitive load. So we can look at your pupillometry, how your pupil oscillates, and look at it in a time window and try to measure it and provide you. So the number's going to change every time. So it's not an easy math to do it, because the way that offline works is very different from how we want to do it in real time. So that's what, Gavindya tried to do here. And, by thresholding, with multiple of derivatives, we try to come up with a single measure for a time window. So when the more data comes in, we use that data to come up with, okay, what is now the cognitive load? The cognitive load can change in real time. So imagine like a pilot, right? So this is gonna be a measure that we can use it to measure the cognitive load in real time.
So this
That is really
visualization, sorry to interrupt. So this
No, go ahead.
visualization might not indicate what you want to see in terms of cognitive load, because we are still working on like how someone who is not aware how to interpret this. So we are still working on the visualizations part. This is rather a visualization of some of the matrix that we generated along the way of generating LHIPA value.
So basically raw data.
Yeah.
And of course, once you do this in real time, then people can start building applications on top of it.
Yes.
Right?
I mean, yeah,
Yeah.
exactly.
I've been hanging out with a bunch of business folks, so that's the sort of thing, that's where their mind would go, I'm sure. That's really cool. Okay, thank you for explaining it.
You're welcome.
Okay, any other questions for Gavindya?
I have a question. So I see that you have noise and probably uncertainties of the data point. I mean, do you know the sources of the noise?
So before we process the data, we remove the noises that's available. What you see here is after removing the noise, the signal that we processed.
Yeah, but still, do you know the sources of the noise?
There could be blinks, they could be not looking at the eye tracker, they could be lighting condition problems.
And what kinds of distribution are they following?
That I did not analyze. The distribution of the noises.
Okay, they might follow a Gaussian distribution, but I'm not sure because depending on the sources. If the source is really random, it may follow Gaussian, but otherwise it may not.
That's a really
the
good
composite,
thing to.
right? The composite of different noise sources might not follow a Gaussian distribution. So, and that's my influence the way you denoise the signal.
Yes, thank you very much, Dr. I think that's a great thing that we should be looking into, because with eye tracking data, we always have the problem of how to remove the noise, how to get the data values that the person is only looking at the screen, because otherwise it could generate like negative values or some random values that we do not want to incorporate in this kind of analysis. So noise distribution, that would be a good thing for us to look into. Thank you very much for the suggestion.
So last quick question is that can denoising real time? Can denoising be real time or no?
It could be, because if we know what is the XY positions, and when it comes to the pupil diameter, we know what the ranges looks like. So if something is off, we can filter them and utilize the other information, the correct information available.
Plus, Jian, the eye tracker can tell us when there is an error, because basically.
Oh, validations. Yes.
You validate. We have a way to measure and validate whether we are getting the data exactly the way that we're supposed to get. Other than the instrumentation errors, but basically we know that what is the accuracy of the instrumentation itself. So that can tell us how much off we are from a data point.
Okay, so there is some model which can be used to denoise it.
Yeah.
That's the built-in, that's a built-in model. Okay, I got it. Okay, thank you. Great job.
Thank you.
Hey, thank you. And with that, I think we'll move on to Yash's presentation.
Yeah. Is my screen visible?
All right. Yep, got it.
Yeah, so hello everyone. My name is Yash Prakash. This is the first time I'm presenting at WSDL, so I'm excited to be here and equivalently nervous. So I'm here to present our paper entitled AutoDesc, Facilitating Convenient Perusal of Web Data Items for Blind Users. So the web has permeated many aspects of our lives and has become essential for connecting with others, obtaining information, shopping, banking, etc. While we all benefit from these online services, their utility is even greater for blind people who often rely on human assistance with more simple activities, and who can now rely on assistive technologies to do them independently on the web. Unfortunately, due to the complexity of web pages and the nature of ever-growing dynamic web pages, and also the limitations of available assistive technologies, blind people often struggle with web browsing and spend excessive amount of time even on simple tasks online. For example, blind people interacting with e-commerce websites in particular using screen readers need to put a lot of effort into web browsing, including going back and forth between data records, comparing data records, searching for data record details, etc. This is because navigation with screen readers is predominantly one-dimensional serial navigation. Although there are keyboard shortcut aids that are available to move around the content with screen readers, the keyboard-centric press and listen interaction model of screen readers is very inherently limited, because it can lead to excessive use of shortcuts even for doing simple browsing tasks. And one has to remember an assortment of shortcut keys and memorize various browsing strategies. And even the serial narration of content may cause a lot of irrelevant content to be read out very frequently while browsing. So to give you all an understanding of how screen reader works on a web page, I will just show you this quick video.
Try free for 30 days. You can save $1,300 plus a year star. You can save $1,300 plus a year star link. Star important details button. Carousel controls navigation landmark play button. Previous carousel slide button. Next carousel.
So you can clearly see, right, or you can imagine that navigation is unsuitable for interacting with web data records, such as search results or a list of items on an e-commerce website. Moreover, if you look at e-commerce websites, information about these data records is usually distributed across multiple web pages. For example, the search results page will have only summaries of items, and the details page, on the other hand, will have more information such as descriptions and reviews related to each data item. So the details page basically further exacerbates the interaction overhead, since blind users have to spend additional time listening to or skipping such content to reach the desired information on the details page. And sighted users, on the other hand, can rely on visual cues to almost instantly locate desired information. Therefore, there is this imperative need to bridge this usability gap between sighted users and blind users on e-commerce platforms. So to address web usability issues, many prior solutions have been proposed, such as Screen Dial, in support, which was presented by Javed in the last WSDL meet. And then you have Dante and you have Sail. So most of these solutions basically target general web usability issues for blind screen reader users. And they provide very limited support for data record specific interaction activities. And to the best of our knowledge, there is hardly any support for efficiently accessing any form of data that is distributed across many web pages, as in the case of data records. So to address this issue, we basically propose the idea of providing instant access to item descriptions whenever a user requests them on the results page itself. So basically what we do is we automatically detect and extract the descriptions from the details page, and then we proactively inject them into the results page so that users can access them whenever they desire. This way, blind users don't have to explicitly navigate to a different page each time to access description of each data item. Such an instant access also promotes a sense of uniformity across different websites, in the sense that descriptions can be accessed using the same set of shortcut keys. So in our work, we basically designed and developed AutoDesc, which is a web browser extension that facilitates easy and quick access to additional descriptions of web data items in order to significantly reduce interaction overhead of screen reader users. We then design a method to automatically identify and extract additional item descriptions from details page of the current website. And then once we have a system ready, we report the final findings to a user study, which we conducted with 16 screen reader users who evaluated AutoDesc. So this figure in front of you basically shows the AutoDesc overall architectural workflow. So when the query results or the search results web page is loaded in the browser, AutoDesc basically leverages the STEM algorithm to identify and extract all web data items and their respective attributes, such as title, price, rating. Following this, the Get Details button is injected into each data item summary, as you can see in the figure. When a user presses this button for an item, the backend that exists in AutoDesc proactively fetches the details page of that item and automatically identifies the item description using a custom-built mask RCN model and extracts the text using a Tesseract OCR engine. And then we finally post-correct the text using a pre-trained BERT. Finally, AutoDesc places the text extracted from the details page right below the button clicked in the query results page, as you can see in the final image. So basically, AutoDesc is a browser extension that allows blind users to peek into some of the additional descriptions about any items in the query results page itself, without having to navigate to a corresponding subsequent details page, thereby saving users time and effort by reducing the number of back and forth traversals between search results and details page. To extract item descriptions, like I had already mentioned, we trained a mask RCN model with our own custom data set that is publicly available. We built the data set because we did not find an existing data set that would suit our requirements. So we use this model basically to extract item descriptions that have some sort of visual similarities across different websites. We built a training data set by collecting and manually annotating instances of different kinds of web pages. from a diverse set of websites belonging to different domains such as business, finance, home, garden, shopping, technology, and computing. And the interesting part in this research was the user interface. So it wasn't direct user interface that we built. Our user interface was basically influenced by prior research work, which observed that in their study, there existed a lack of awareness and shared design guidelines for visually impaired folks in the e-commerce community. They then proposed three design principles, which is basically uniformity and coherence, navigation, and logical provisions. Most of these designs were given by performing expert analysis of current user experience and by following existing guidelines through the W3C consortium. So once we had a system ready, we get into the user study phase. So in the user study phase, we basically evaluate our system. So we conducted the user study with 16 blind participants, where 7 identified themselves as female and 9 identified themselves as male. The task was to peruse a list of data records on a typical e-commerce website. The study basically had 3 conditions, right? The first condition is the default screen reader condition. So participants basically do the task on web pages that have not been externally enhanced for any form of usability. And the next condition, the next condition, participants basically do the task on web pages that have special ARIA landmarks injected by a state-of-the-art method called SAIL. So what SAIL does is basically it uses visual saliency model that has eye tracking data to find different salient parts of your web page or different salient segments of the web page, and then you inject landmarks at the beginning to each of these segments so that users can quickly navigate through these segments using special shortcut keys. And lastly, we tested our AutoDesc prototype. And to mitigate the learning effect, we did not use the same website more than once while doing the task in different conditions. So the figures in this slide basically shows the end results. The first 2 box plots show the average time spent per item and the average number of shortcuts used per item respectively. The next 2 box plots show the average number of distinct items that participants covered in the task and the average number of items that the participants navigated, the average number of times participants navigated back and forth between the search results page and the details page. From these box plots, we can clearly observe that AutoDesc showed the best performance for all matrices. The difference in performance values between AutoDesc and other conditions was also found to be statistically significant. More details comparing the performance and underlying reasons for various conditions that were set during the study have been mentioned in the paper in detail. So again, for all the 3 conditions, we conducted 2 other studies, that is the perceived usability SUS and task workload NASA TLX, where the best in Autodesk condition, both the results were the best in Autodesk condition as compared to the other conditions, that was default screen reader and SAIL. So the SUS questionnaire asked participants to rate alternating positive and negative Likert items on a scale of 1 to 5. 1 being strongly disagree and 5 being strongly agree. The responses are then combined into a single score, which ranges from 0 to 100, with higher scores indicating better usability evaluations. We then administered the standard NASA TLX questionnaire to gauge the workload experienced by participants while they did the assigned task in different study conditions. Like SUS, NASA TLX also generates a score between 0 to 100. And here in SUS, it was to evaluate usability. Over here, it is to estimate the perceived task workload. So you can note that in the case of SUS, high score basically indicates better performance. And in the case of NASA TLX, lower score indicates better performance. Among 6 subscales used in the NASA TLX, mental demand, effort, and frustration subscales contributed to higher workloads in screen reader and SAIL as opposed to our system Autodesk. So this is the most interesting part in the entire paper. So you basically build a system, you call users, you perform the user study, and then you gain qualitative feedback. So our participants provided us with various qualitative feedbacks. Most of the participants said that it was tiring to explore data items with screen readers because it is a tedious process. They also mentioned they usually only explore the first few items in the search results page, and so they often miss out on good deals. A majority of participants also mentioned that as they couldn't remember many details due to content overload, they had to revisit item summaries multiple times, which further exacerbated the usability of interaction because of numerous key presses that they had to perform. The participants mentioned that AutoDesc helped to reduce this back and forth navigation quickly and help them to quickly filter out the items that they don't prefer with very much less effort. The participants also showed their support for other, also stated that it would be great if we could provide support for other data record information such as reviews and product comparisons and table of content that exists in the details page. So although there were many positive outcomes of our work, there are few limitations that we listed and explained in the paper. So a brief of, and these limitations basically will direct our future research in this area. And these limitations basically include that we only looked at websites where both SAIL and Autodesk algorithms could correctly find the item descriptions on the details page. And then Autodesk only gets information or item descriptions ahead of time. Some people who took the part in the exit interviews also mentioned that they would like to have instant access to other informations about the item, like reviews, suggestions for similar items, comparisons of 2 or more items, filtration of items, etc. And ultimately, Autodesk works only in the Chrome web browser. The GitHub links and the dataset links, all of them are publicly available. So in this paper, we basically seek to bridge this divide for an important web activity, right? That is interaction with web data items by facilitating more efficient and usable interaction with the contents of web data items. We envision that blind users too will be able to explore more data items in a short duration with very less effort and score better deals similar to their cited peers. So this basically concludes my presentation. I thank you all for your time and attention. I can take the questions now.
Hey, thank you, Yash. Yeah, any questions for Yash? So Yash, can you go back one slide, please? That's your final slide. Never have a thank you slide.
Oh, okay. Yeah.
Yeah, this is a slide that you want everything. It's got your results, your URLs, everything. You can say thank you on this slide, but you know, have this one be your last slide. So my question was, how could you combine what you're doing with, say, Travis's approach, where we could automate this procedure, gamify this procedure, perhaps have a competition between either different algorithms, different screen readers, combination of algorithms and screen readers, time to complete a task, you know, something like that. Could we have a gamified approach to this?
We could actually, I mean, that is an interesting question. So if you look at this entire paper, we build it as a Chrome extension. So whenever we take like a Chrome extension approach, it's basically we have to augment the web. The screen reader functionality is still it's still rudimentary. So if you can build an intelligent screen reader, a screen reader that can understand users' needs to basically perform certain tasks on the web page, you can have a gamified approach over there, where your whole narrative is not about changing or augmenting the web page, but your whole narrative is to create some form of an intelligent screen reader that can follow that gamified process to, for example, you know, if there are multiple extensions, if you want to select any extension in particular, you can have a gamified approach over there. So if you want to follow that approach, the whole control of your system should be on the screen reader's end. It cannot be on the website's end. Or like the extension approach will not be that feasible.
Okay, excellent. Thank you. Any other questions for Yash? Matt had a question.
Yeah, I can just say it. So I'm thinking of when the Web Accessibility Initiative was first kicking off, and they encouraged online sites to annotate their markup for the sake of accessibility. JAWS being sort of the fundamental examples. So with that in mind, from the perspective of online retailers, is there anything they can currently do to make AutoDesc features, more useful, I guess, on other sites? That's what I'm trying to say.
Yeah, so there are multiple accessibility standards by the W3C consortium. JAWS does have certain, so JAWS, all the functionalities that JAWS has in terms of the shortcut keys is very limited to one particular web page. If we have to extend the same functionality into multiple web pages, I don't think JAWS will be able to perform that particular task. So if you want to do something in multiple web pages, you'll have to actually reload the other web page. And on that web page, you can use some shortcut keys to navigate through that web page. But again, that is more of an accessibility thing. In our whole project, it was more of a usability issue that we wanted to solve with multiple web pages. So to answer the question again, to concise it, there are accessibility standards, but and JAWS has a lot of shortcut keys, but most of them are limited to a particular web page only. You can't extend that to a similar web page, to another web page or a subsequent web page. If you move to the subsequent web page, you'll have to perform the same shortcut keys all over again. That is the problem. So it is always good, like in our project, if you have like one data record and if you have information related to that data record in the subsequent web page, you have a lot of information over there. It is better to summarize it and get it into the first web page itself. So you can maintain, like our user interface was basically designed based on prior research on accessibility itself, where it was the only paper actually that mentioned accessibility problems in e-commerce. That is another problem in this research, that if you look at different ecosystems, right? If you look at, let's say, hotel menus, or you look at education platforms, or you look at e-commerce platforms, each of them have their own accessibility and usability issues. You cannot generalize accessibility and usability across the entire web spectrum. So there's only one paper in the e-commerce spectrum which address accessibility, and we did leverage that. But again, it does not work across multiple web pages.
To add to that, basically to clarify, so Matt, the whole thing is even if content is accessible, it's simply too slow and too frustrating for blind users because of this one-dimensional navigation, which are like press and listen. So, and the content, such as in case of data records or data items, is like simply scattered over multiple web pages, and going back and forth between web pages is simply not too, practical for like long-term exploration of these kind of web content. So what we were trying to do is address that usability issue. Accessibility issues, what JAWS does is just to make things accessible by having proper headings and injecting some kind of ARIA landmarks. Those are there, but they still don't help speed up or make it easy. You can still listen to everything that's there on the web page, but the process is simply too slow. And you cannot carry over navigation strategies that you develop, the keyword navigation strategies. And in one web page, the HTML is different. The way web data items are implemented is different from the way it's implemented under the hood in HTML in another e-commerce web page. So what that means is, let's say you had some strategy that you developed over time on Amazon, which helps you use some cleverly use a set of shortcuts to access different information quicker. You cannot use the same strategy in another web page. So for every web page, depending on how the developers have implemented it, you have to design new strategies. And this simply is not, practical. That's why they sort of stick to one or two web pages, and in that process, they miss out on a lot of deals like we sighted people enjoy. Like we compare the same product to what is the offer in different websites, and we try to pick the best one, right? So that is cheaper most often, and also we get a good deal. So blind people are missing out on that. So we wanted to address that in this paper.
So Sean, you had a comment in there. I think you intended as a joke, but there could actually be something in there. Did you want to say something about it?
Well, at first I didn't think of it as a joke, and then I realized it could be a joke, considering all the buzz about
Now it's
ChatGPT at the moment.
back to being real.
Oh, yeah, that's the thing. Is I mean, yeah, you could attach like a large language model to this to somehow, essentially, once you've extracted the information, make it more presentable to the person who's consuming it. I don't know how you do that, but that's what I was thinking initially with your information extraction step, especially considering you're trying to provide this information in a more meaningful fashion so that someone could take an action on it. The problem is large language models have a tendency to lie. So I don't know if that's a problem with the small amount of data here, but it's something you might want to at least consider in your future work.
Yeah, you don't want the language model to lie about the price of the ticket, right?
Exactly. Yeah, that's the problem.
The GPT large language models can be used at the interface side. So each of these works that we do to improve usability, they have like a backend, which is more concerned with extracting data and making sense out of it and representing it in some abstract way. And then there is the front end that takes this abstract representation and presents it to the blind user in a particular way. What we did here is just show it in like an iframe or something, right? Or a very easily accessible and navigable div with keyboard. So we tuned the front end for the keyboard interaction. So if you replace it with some kind of dialogue interaction, then yes, we can leverage some kind of natural language generators, right? Which take some kind of abstract information and then creatively create some kind of sentences that look natural and give all the information to the blind user. So it's just a matter of interface development. So we can connect large language models at the interface side.
True. And I can see how the keyboard interface would be a lot better for someone who's just trying to get through a site and get the information they want. Whereas large language model, I get tired of talking to Alexa. It's irritating. Not that I do it that much, but the point is yeah, I can see the benefit of the keyboards. I wasn't sure if maybe there was a case where one could use that. Again, I thought of the idea seriously, and then I realized that it probably isn't ready for this application yet because of the issues with the language models.
So my dissertation long time ago was on building some kind of speech assistants, long before these, for web browsing. So long before these, large language models, transformers, none of them existed at that time. So one of the things I noticed, like in actual studies with blind users, is that they like speech when they are specifically interested in some small portion of information in a large setting, right? For many other cases, keyboard is faster, like pressing 4 down keys to to listen to information that's locally salient, like close to each other, is much faster than asking for each individual information. Like you see in a data item, there is price, there is a whole bunch of other attributes like ratings and shipping and all that. So it's faster to press down and hear all of them, rather than saying what is the price, wait for it to give you the result, what is the rating, wait for it to give you the result. So this kind of back and forth is tiring with speech, although speech is considered to be convenient, but it's not true for all cases. So if they want something
I agree.
If they want something like, okay, what is the cheapest item, there they like speech, because now to find the answer for that, they need to go over all the items. And that's where speech has, preference over keyboard. Like they prefer speech over keyboard, right? So speech, they mostly like it for like some kind of global information access, something that sort of says some characteristic about the content. For local access, like local neighborhood, they still prefer keyboard because it's faster.
And I have to agree, especially with Michael Nelson's comment here about keyboards and command line. As a VI user, I find it's faster for me to edit files just using the key presses rather than using something with a mouse or whatever. So that's even more extreme.
So yeah, I could see how it would be very tedious to just be talking to it in order to try to get the information you would want out of it. So yeah, food for thought.
So thinking out loud here and combining the concept of the vision tracking talk that we had a moment ago, and this thing for people without vision. What if we take a web page and render it in a viewport of a web browser virtually, and then allow people to just navigate, as you say, not just down, but left, right, down, top corner, bottom corner, or whatever is scroll further down or something, as if they are kind of saying this, and there is a mouse cursor who is moving all over the page. It doesn't have to be like jumping from one link to the other or one button to the other, just the screen real estate. If it is going there, there is a spotlight area, say a rectangular or circular area around it, where we have whatever is the highlight of that region, what is there to be seen or known or understood, like, that can be communicated. That can be described in just few words, basically. And if they want to drill down deeper, they can kind of expand their the diameter of their focus, basically, in that region. So this way, kind of giving them a sense of 2D exploration. They don't have to go linearly or jumping from one area marker to the other, basically. Just kind of perceiving the rendered page and describing that.
So that's already there, actually. Screen readers do support. It's known as like some kind of cursor navigation or touch exploration on phone, based on where your current mouse focus or your finger is. It'll read out whatever is there under the focus, like under the cursor or under your finger. So that is there, but it used to work before when the pages were not that dense, so to speak. But in my own user studies, I've seen that these blind people just hate it because it's just content overload, right? So they hear a lot of things as the mouse moves. And since they cannot see the mouse cursor, they cannot control its direction. So it's basically they have to listen to a lot. It's the
I was actually, so what I was proposing is not to read everything that is there, kind of synthesizing it and announcing just the highlights and
they have tried to do that, but then again, the diversity is the challenge there. I'm not saying it's not doable, but it's the challenge. Like, you have to define how something will be presented, like voiced out. And then you'll have to look at the semantics of each portion that you're trying to voice out, wherever the mouse cursor is and that region of interest, so to speak. Right? So
I think there is an opportunity to, again, the route that, say, large language models take. You don't have to be super accurate or kind of be exactly precise, but synthesize something that is more consumable. And if they want to be, if they show interest, like, yeah, this sounds like it's a region I need to pay attention to, then go deeper and do as accurate as possible. But kind of just moving around and say, hey, here is an ad. Basically, you can skip it. Move in this direction. There is a bestseller badge on this one. Maybe you want to pay attention to that, something like that, right? And not reading out everything. That's something that would be really problematic.
You're absolutely correct. So there have been papers on that, including my own, wherein we just sort of give some kind of summary.
All right, guys, I'm going to jump in. This is a good conversation, but we need to move on to the next talk. All right, David, are you ready?
Hi, everybody. Yep.
All right.
Go ahead and screen share here. Okay.
Got it.
Okay. So everybody, I'm David. I'm going to be presenting some updates I've been working on to the Memento damage service here with Dr. Nelson and Dr. Weigel. Okay, so for those who kind of just real quick who don't know a web archive, a work is an ISO file format that allows a web crawler to go out and request a web page and get the response, and then write that to a work file, and then subsequently go and do the same thing for the content of the web page, to request the page's content, get the response, and write that to a work file as just one nice kind of neat package that can be replayed later. But once you have that and you replay it, how do you know how well it was archived? Well, that's where the Memento damage service comes in. Over here, started by Dr. Brunel, who's in our chat over here. So in this case, it breaks it looks at the page and kind of breaks the page apart into different components. It gets a score for each of those components, which then adds up to one total damage score for the page. In this case, the service can look at pretty much any public kind of URL, but specifically, it's kind of geared towards archive pages, but it can look at the live pages as well there. So damage is scored differently on pages based on the content. In this case, we have like an example of an XKCD comic page, which has the main webcomic, the banner logo for the website, and just some links with images to other ones there. Which each of those would have a different score kind of based on their semantic context within the page and their location. And then it goes, of course, how many would be missing. Here we have an example of just two websites, each missing two CSSs, but the one on the right is noticeably more intact and less damaged than the one on the left. So they're just kind of some examples of damage that can happen to a web page. Now there's some stuff though that is kind of outside the scope of the Memento damage framework, such as kind of temporal violations, where we're really trying to look at just the web page itself on its face and kind of see like what's missing and how important those are. So when you kind of get to the like JavaScript aspects and just different things getting loaded for different kind of time periods, it's kind of hard to check that context with things like Memento damage would be a little outside of the scope, or just need to be extra stuff kind of coded in to take into account this stuff. But really trying to look at just kind of the web page itself. Now, from Dr. Brunel's dissertation here, we can kind of see that the JavaScript, the resources being loaded with JavaScript has just been increasing over time, as well as kind of affecting the missing JavaScript that's returned from the page there. One of the things that they found when they were going was crawling stuff was to use kind of their own Phantom.js crawler to kind of help with some of the stuff compared to the open source Heritrix crawler from the Internet Archive. While it's a lot slower, it was able to grab a lot more URLs. Now this was when I came onto the project, this had kind of been deprecated already in 2018. So I kind of came around and rewrote the Phantom.js stuff in Puppeteer, which was spun up by Google, and it's very kind of tied in with Chrome or Chromium. I use a Docker container that's kind of all built in with it because they kind of update it in lockstep. It's not really meant to be like a separate thing or just run on its own outside of kind of Chromium. It's meant to be built with very specific versions. So I found the best way to kind of work with that is to use their kind of integrated Docker container for that. And I've also been working to kind of update it to handle like batch URLs and stuff if you pass it in over the command line. But kind of the problem you run into with that is, especially with the Internet Archive, you're rate limited still as to how many things you can actually crawl and resources you can get in a certain amount of time there. Now kind of once you have your pages and you're looking at it, Dr. Brunel kind of assessed the heuristics by which different components could be scored. And then again, kind of all brought together to have one total score or one total like normalized score from 1 to 0 for the page as a whole. When I came in, we kind of started working with the Collaborative Software Archiving for Institutions project and taking that work and kind of specializing it a little bit more specifically for kind of Git repositories or just like Git hosted platforms like GitHub, GitLab, Bitbucket, SourceForge, things like that. And specifically, we're working with a kind of tool and trying to get it kind of integrated in with this tool called Memento Tracer, which is able to get tailored captures based on like a user selection. So let's say you only want, you're looking at a GitHub page and you only want to get the README and you want to get the file list, but you don't want anything else on the page. You can kind of select those things and only capture those, and have a subjective quality depending on who would be the person capturing it, like what you intend to capture and what's important to you, but kind of save a lot on space and still have the capture there. And on this project, we're working, of course, with Dr. Nelson Weigel again, as well as Dr. Martin Klein from Los Alamos Labs and Vicki Rampin from New York University Libraries, as well as Emily in here, and some others, Talia Cooper. Now, we kind of still have a lot of the same issues with JavaScript when you're looking at archive. Now, ironically, a lot of it's static files, so it's kind of, there's less damage overall to the content that's being added, but you still have JavaScript being loaded all over the page for various things, like these little shield buttons to return little images, trying to get commit information that's trying to load from the server, as well as things like branches and tags and things like that don't always work. Sometimes in the case of the top left over here, we're missing the entire avatar for the person who committed. And in the bottom right for the contributors, we have 3 of the avatars that loaded, but we're missing them for most of the people there. Sometimes this is just like the Internet Archive and trying to load slow, and sometimes they just never load. So that's kind of like a toss-up. Sometimes it's been difficult to tell which it is all the time when you're trying to assess damage. Sometimes they just load incredibly slow and slower than the crawler or the puppeteer in this case is programmed to kind of wait for them. So you don't want to sit there and wait forever for some of the resources to come back. Now also some of the pages are kind of their own special source over here, like SourceForge is, they don't always have a Git. Not all their software that's uploaded has an actual Git. Some of them do, and when they do have it, sometimes they're all kinds of special and different in their own unique things. They also kind of deliver files a little bit different than the other repositories do a little bit, which kind of makes it hard to tell, you know, if like a file is available in the repository, like at a from the Memento damage service, without going through like interstitial pages, which ultimately leads you to our URL over here, our broken URL over here. Sorry. There's also cases of some kind of obscure damages with the README or the Markdown format a little bit. I'm sorry, where the images in this case are missing, but it just defaults to text. So if you're just kind of skimming through, you might just think this is just a regular link that you got to click on mixed in with the other ones, but these are actually just missing images that should be in there, which is kind of one of the biggest chunks of damage for some of these. Again, it's kind of, they're static files, so they're relatively uniform, but a lot of the times just missing links that were put in there from people where they didn't update a link through commits or some of the stuff on the page. But specifically with the software repositories and looking at kind of updating Memento damage a little bit, like taking stuff like this and specializing it where the content that was added by the person who's committing to the README is probably a little more important than just some of the avatars and stuff around the page that might be generated. With software repositories, there's also a lot of extra ephemeral things as well. There's like the wiki, there's the issues, there's all kinds of other pages that go along with it, not just the main page there. So those are things we're like looking at and taking into account as well. On top of these software repository stuff, I've been looking into kind of updating and just trying to experiment with getting some more accurate, some better damage values out of the different things on the page. So for instance, one of the heuristics for the images was looking if it crossed the center line of the page. But sometimes I found that images it'd be the only image on the page or one of the only two or the main focus of the page, but it wouldn't cross the center line, so it wouldn't get triggered as important. Or if it's missing and it doesn't have a size attribute that we can check against if it's going across the middle of the page will just render it as a tiny little missing icon. So it'll take that as the size rather than the original size that it should have been. So maybe it would have been important, but if it's missing, it's hard to tell because the size just rendering is really small. In that case, also you can kind of look at things like the size of the parent container to maybe not use the whole size of it as the damage, maybe take a mean or just some kind of other approximation based on the size it could be of the container. And also things like the contextuality of the sibling elements and things like that. So if in the case of the bottom one, we have like just 4 little example icons. If they're all the same and they're all the same size, we could probably estimate that one of the missing images is probably the same size. But if they're all different sizes and they're all different, we can't really get that context by looking at those different elements there. I've also been working on trying to make it a little more the visuals for the damage a little bit better, kind of at first glance. Now, in the case of the right over here, it's the USGS page is missing 2 main images. In this case, I've kind of got 2 damage highlight boxes with different colors and opacities, kind of just representing how much damage there would be for those different elements. And then over here on the left, I've made it as a mode. So when it goes to highlight the damage and annotate the whole page, it also goes and would create these little highlight boxes of it would take just the damaged area and just have a little buffer zone for visual, just to make it a little nicer to look at there. And then just try to give it, display the damage score with it. Now, in this case, these are the ones that are really small. So if we were to look at a very kind of big page like this, or even longer on a GitHub, sometimes the README can be just like a mile long, depending on how much content is there. If you're just looking at the whole screenshot, it can be really hard to kind of see like these little damaged areas here. So that's why I try to have their own little highlights as well as just the main screenshot. And for this one, like they kind of worked out where the opacity is a little bit better to look at than just like the text over here, because sometimes the text number could be a little bit small for that as well if you're just trying to like find it on a page and pick it out of a whole giant screenshot. One thing I've also been recently looking at is maybe kind of taking some of the content and filling in what's missing a little bit. So this is a case where there was a GitHub page that had a bunch of different kind of clusters of images. And like half of those clusters had 1 or 2 missing images in it. In this case, it was a cluster of Eiffel Towers. So what I did was initially I looked at a service called, it's called Clip as a Service by Gina is the company, Gina.ai. And they have a cool little pre-built data set of a broad amount of images, but it's not a whole lot. So if you try to give it this and get an image back, kind of works, but it's not very accurate. Microsoft Visual GPT, they actually renamed it to Task Matrix recently, is what this is. Unfortunately, though, this kind of costs some money to do. You have to have an OpenAI API key to run this, which is going to cost you a little bit of money every time. So ultimately, it's not very feasible in volume to do this, but it's kind of a cool study where we could take some of the images that are present on the page and try to kind of fill in what's missing a little bit to help improve the visual fidelity of the page just when it's crawling. Not permanently kind of embed it back in, not just add something that wasn't there, but just as a temporary kind of thing, just to improve the visuals and stuff of the page a little bit. Now, so some of the other research that has been going on recently from when Dr. Brunel first started finished his dissertation, and a little before I came on, was this paper out of Germany by Kiesel and other researchers, where they were trying to get an automatic quality assessment of Memento damage, or of just the playback of archive page there. And they were able to get better improvements with their own custom implementation over WorksProx and PyWB for playback. But if we look over here at Dr. Brunel's measurements, it's different than the other two, because the other two over here measurements are actually able to kind of cross-check with another page, whereas the Memento damage service is just kind of trying to look at the damage on its face without any other outside comparison. So it wasn't able to kind of get as good of a score as the RMSE comparison or the neural network model that the researchers here had tried to implement. There's also this other paper that is called JavaScript Aware Web Archiving, which kind of takes, instead of the WARC format, they kind of made their own, which tried to eliminate a lot of the problems that JavaScript was bringing in. And essentially what they tried to do is they tried to go and find all the JavaScript calls on a page and trigger them at least once to see, what would happen and what stuff would get back. And they were able to reduce the overall size and increase the throughput compared to, they use ArchiveBox as kind of a base for their crawler. And they were able to find that they found that they were able to reduce the storage of a lot of things for the Internet Archive by 41%. But again, it's using a whole different format, so it's not exactly one-to-one with work, and maybe it could be worked in later, but that's something you have to kind of migrate over to if you wanted to have like this level of fidelity with stuff. Now, kind of going forward in the future, again, you're kind of limited sometimes by rate limiting of where you're crawling. But if you just, let's say you have like tons of your own works, one of the things that we really kind of want to go for is just speed, of course, accuracy, but speed and volume, being able to like calculate the damage really quick for a lot of pages rather than just like one at a time. And there's using things like big data tools like Archive Spark and Common Crawl data, which just has massive data sets you can kind of look at. Are kind of ways I think to go about this in the future. And then this going towards a machine learning approach. I saw this WorkDL paper. It's like a one-page kind of paper that just lays out a framework for working with works in a machine learning environment. So this is something that would be probably useful to go implement as well in the future with the previous two papers and other big data tools to, again, kind of increase the scope and speed at which things can be checked in a more automatic fashion than just one at a time or just a few at a time. And then if anybody has any questions about some of the papers here, here's all the links right here that you can go check out. Especially, so Dr. Brunel had a post also contrasting his work with Dr. Kiesel's paper a few years ago. I think that's a really good place to start on a lot of these resources here and some of the updates we've been working on. Sorry, kind of does anybody have any questions?
I think I have to. I think I'm like obligated to ask questions about this. So, in hindsight, this is probably, this entire like problem is probably a few dissertations of research topics. And I think you highlighted something really insightful, that there's probably categories of damage that again, in hindsight, we didn't even consider, didn't address, that the new ways of building client-side web pages is shifting. So I guess, do you have a view of where are the high priority targets for those types of damage, and are there things that the original paper maybe didn't address that you think should be addressed as a next step?
Well, so with the COSI group, we were talking about, because there's so many like random little nuances with software kind of repositories and like Git and things like that. But not so much Git, but like Git hosting platforms and where you would see them, that we were talking about maybe kind of some kind of separate module for those or something like that, or kind of specialized, like some kind of specialized module that, I guess could be abstracted out to just a broad subset of different web pages, like one for Git platforms, one for like news articles or something like that. They could specialize for each maybe, or, just templates kind of, I think would be a better way to think about that. So far, we were just really looking at the software repository stuff, but it could definitely be, pulled out for other ones. I think though that a lot of the other research seemed to kind of go a little bit away from the heuristics, which would be interesting to see like how that would develop if we go with a template route versus just trying to like some kind of automated machine learning. Like, I feel like the templates are a great way to go, but I just worry about maybe getting bogged down with it, or just having like a template for everything, and then somehow you just have to roll it back into the core of the source anyway, like into the heart of it kind of. So there's stuff like, there's always like little nuances like that.
Yeah, totally tracking. I think that you're keying into some stuff that we again probably didn't know enough about to think to look at, right? Of looking at the templating. I think when you look at some of the other research that's been presented this afternoon, figuring out eye tracking, targets on a page, what effect that has on importance. Looking at the ability to backfill a particularly damaged memento with a different type of crawler that performs well in different gamified scenarios. I mean, there's a lot of really cool directions I think this could go in, but all of it, kind of keys into exactly what you're talking about, right? Of there being these different use cases that are going to demand different heuristics and investigations. So I think this is really cool stuff.
Well, coming for you, that's a big honor there. So thank you.
Great. Matt, you had a question as well? Question?
Yeah, I had a question. So you said in one of your future works coming up that you were to consider, for instance, what was when you were talking about the missing avatars and the GitHub interface as to whether they were important, whether we could have substitutions on there. And so you said something about looking at the what was viewable or not. But as we know from a bunch of WSDL work and elsewhere, that representation that you're seeing there is going to be dependent on the user agent that you use. So for instance, if you view the same page via mobile or simply your viewport is smaller, you're going to get a different set of resources on there. So what do you expect to use for? I know you can probably just use 1040 by 768 or something like that for the size, but what do you want to use for the canonical user agent and viewport size? What are going to be those facets that you're going to use as a basis for determining whether or not something is missing? That's what I'm asking.
So essentially the way that the crawler operates, I didn't really code, I kept it the same. I just kind of updated it and migrated it to Puppeteer, but the way that it looks for stuff and crawls is the same. It still uses the 1080p resolution there as its resolution for crawling. And still just a desktop landscape orientation there. I haven't tried to do it with a mobile or anything yet. One of the things on my list is since Heritrix has been updated a whole lot since that, I want to kind of go back and get some benchmarks on that stuff. And I probably when I do that would maybe be a good time to set it to mobile resolutions and stuff and see what different results I get for that for the large volume testing.
All right, great. Thank you, David. In interest of staying on time, why don't we go ahead and get started with Kenny's presentation?
Thank you very much, everybody.
Please let me know if you can see my screen.
Looks good.
Oh, okay.
All
right.
Slideshow. There you go.
Yeah. All right. My name is Kehinde Ajayi. I usually go by Kenny. I'm a PhD student in the computer science department. Dr. Wu is my advisor, and I'm here to present one of our work on a study on reproducibility and replicability of table structure recognition methods. We're actually presenting this work at the 2023 International Conference on Document Analysis and Recognition. That's the IGDA 2023. Okay. So just to give some background, so reproducibility here, we're majorly defining it as a method of obtaining same consistent computational results using the same data, the code, the condition of experiment as stated by the original author. While we defined replicability as also obtaining consistent results, but instead of using the same data set or the same data set as used by the original author, we're using a similar data set. But the method, the methodology, every other the conditions of the experiment remain the same, but just the data set, and the data set is still similar. Okay, so one of just to talk about some of the motivations that are behind this work. So our research, from our research we saw that most of the current studies actually focus on the availability of code, whether codes and data, the URL linking to codes and data are available in a research paper, one of which was done by Lamia last year, and also some studies also focus on where the documentation of the experiments. Okay, so whether the experiment or the methodology have a detailed documentation. Some studies focus on whether the codes included by the that are included in the paper by the author are executable. However, only few works actually directly reproduce the methods, the published findings by the authors, and the actual part we focus on is on the replication, because this was actually rarely conducted, which is, like I said, as I defined in the previous slide, obtaining consistent result on a similar data set. So, and we might wonder why this study, why it actually matters to focus on reproducing AI papers or even replicating it on a similar data set. I mean, we all know that AI are being used a lot in downstream stacks and in other many applications. So it's actually needed, to know, to ensure that this, whatever technology we're using is reliable, is accurate, and is effective for the task, for the specific task that we're using it for. So as a use case, we focus on a subdomain of document analysis known as the table structure recognition, known as table structure recognition. Now, this falls under the table recognition as a whole, where table recognition focuses on two major parts, which is the table detection and table structure recognition. So table detection is more focusing on detecting the tables in a document. Now the document, in a digital document, it could be an image, it could be PDF. Now, but this study majorly focused on the second part, which is the that after detecting a table in a digital document, how do we identify the rows, the columns, and in this table? However, we're also limiting it to not PDF, but a document image, right? So in a TSR, which I call the table structure recognition, the output can be in an XML format, it can be in JSON format. So it's up to the user to determine the format of the output, but it's specifically focusing on identifying the rows, not really extracting the data in the table, but the bounding boxes, the coordinates of the text in that table, right? So, and one of the reasons we chose TSR was because recently a lot of methods have been proposed on TSR, which supposedly achieve a good result, but we found out that most of these methods were not evaluated on the same data sets. And that's because it's currently there is a lot of challenge in getting data sets, like a recent standard data set that the researchers or can actually compare the results on. So we saw that most of the papers, most of the research done were actually not using the same data set. So we used these two standard benchmark. That's the IGDA 2013 data set and the IGDA 2019 task B2. So we focus on these two data sets, which were obtained from the open competitions, which were obtained from the open competitions usually organized by IGDA, right? So these are the two data sets that we use as a standard benchmark. And then as I move on, I will talk about the third one that focuses on the reproducibility. So for this study, we actually measured this research on these research questions, like whether a particular research actually has the data and the code accessible by the user, whether the methods proposed by the original authors are actually executable without reaching out to the original author. We also looked at so we defined our criteria for judging whether a research, a TSR paper is reproducible. So we looked at, we investigated this method based on the criteria that we defined, which I will talk about in a minute. And then we also looked at, okay, if a paper is not reproducible, what are the possible results that could cause this irreproducibility? And then the other part, which is the replicability study, this is where we introduce a new data set, which was created by ours, and also on a similar data set, which are different from ours. Okay, so just talk about the workflow. Specifically, this is the workflow of our research. So we started by sampling the data set, like the papers. So we downloaded 25 papers specific to table structure recognition, but we narrowed it down to, because some of those papers were not applied on document images. So we narrowed it down to those methods that use deep learning and focus on document images. So our sample actually contains 16 of those papers. Then we inspected each of those papers to search for the code, the link to the code and data sets. So for those ones we found, we downloaded them and deployed them locally. We created a virtual environment for each of them to prevent package conflict. And then we conducted these two tests, the reproducibility test and replicability test on each of those papers that we found the code and the URL. So for the reproducibility test, so we actually have a final result that either a paper is reproducible, is partially reproducible, or is non-reproducible. So for the reproducibility test, we actually use the same data set as used by the original author. So our criteria is that that code, for a paper to be reproducible, the codes they have to be executable without any error. And it also, the discrepancies between the author's original result and our reproducibility experiment has to be within 10% of F1 scores. And that could be absolute value. So it could be below or above, within 10% of our F1 score. So that we judge as reproducible. For the papers that have, so for any paper that obtained where our own results are reproducible, reproducibility result appears to be above what was stated in the paper, we judge that as being partially reproducible. And that still have to maintain this criteria of 10% deviation of F1 score. Now for the replicability test, this is where we looked at similar data sets as compared with what the original author used, and then we also use our own data set, which we call the GenTSR. I'll talk about GenTSR in a minute. So the same approach, the same criteria follows suit for the replicability test. So is either a paper is conditionally replicable, if at all it's not replicable to all of the domains in our own data set, or is non-replicable, focusing on these same criteria. Okay. Yeah, so just like I mentioned earlier, we have these are the benchmark that we use, the IGDA 2013, which actually contain tables from the European and brought from the European and US government website. The IGDA 2019 contains two type of data set. We have the modern tables and historical tables. Historical tables are majorly handwritten tables with handwritten digits and letters and all of that. So for the papers that we that finally got into our samples use the modern data set. So we did not use the historical ones. Then the GenTSR is our own data set. Is, as you can see, is more than the IGDA 2013 and 2019. It consists of 386 tables, which we crawled from 6 scientific domains, 3 from the STEM field and 3 from the non-STEM field. And you can see the distribution as displayed here. So by all, in all respect, our data set are actually more than the benchmark. Okay, so and we we've also made this data set publicly available in the and this the link will be, can be gotten from our paper and all of that. So these are the three. So the GenTSR majorly focuses on the replicability test, right? So then I move to the result of the research questions that we did. So the first one was we're looking at, like I mentioned, whether the paper contains the data, like whether the data and the code are actually accessible, like whether the paper that we downloaded contains codes and data that can be accessible by the users. So we found out that out of the 16 papers that we surveyed, we sampled, eight of them actually made their source code available. So why the other 8 are not do not contain the codes and the data. And just to say that when we search for the codes and the data in the paper and we couldn't find it, we also proceed to search online to see, and also the author's website for any means to maybe the author put it in their personal website or online. But for these ones, we couldn't find any of that. So, and then, so among the remaining 8, 3 of them made just only the code available, and only 5 of the remaining 8 made both the code and the data available. So this was really, and our goal, like we said, the criteria is without communicating with the original authors. So we focus on the 5 ones that that made both the code and the data accessible, right? So then we looked at whether the accessible methods, whether they are executable, whether the codes and the data are executable. Okay, so, and then we realized that only 5 of those papers, like I mentioned previously, were executable without contacting the original authors. And but there are 6 of them were not executable. So even though they contain the codes, they were not executable. So that means there were some errors at some point while executing the code, right? So, but there was one that had path issues. So because the issue was not a major one, was path issue from the part of the authors. So we contacted the authors via the GitHub just to figure out, okay, because we realized the error was minor, and then we wrote code to correct that, the data path and all of that across all the codes that for just one author. Okay, so just before moving to the result of the reproducibility, I just want to say that the metric that we use for the reproducibility and replicability is the F1 score with the IOU, that's the intersection over union, which is a metric that is popularly used in object detection domain to evaluate the performance of an algorithm in detecting objects. Specifically, we compare the F1 score obtained from our own experiment with that of the author using the same threshold that was used in the original papers. Okay. Moving to the reproducibility results. So we, out of the 6 executable TSR methods, we found out that only 4, so only 4 of them were reproducible. Let me quickly explain what the notation we have in this table is. So the F1O just stands for the F1, the O stands for the original, meaning the F1 score from the original paper. That was what was reported in the paper. The R0 means the F1 score from our own reproducibility result. So as you can see, there was one paper that our result was actually was better than what was reported. And that could be due to some reason which I will highlight in a minute. So the delta naught is the discrepancy I mentioned before, which is the absolute difference between what was reported in the paper and what we obtained from our reproducibility result. So, like I said, we only judge the papers that have this discrepancy, the delta naught, below within 10%, 0.1. Okay, so that could also be, you know, a large threshold is subject to that. Now, if we look at there is one of these paper that we saw that we couldn't reproduce. That's because that's the splurge, because the author did not make the data set used for the evaluation publicly available. So we couldn't reproduce that. But the code were actually executable, right? So for the research question where we examine the reasons that could cause some these papers to not be reproducible, the first reason here is actually where most of those papers fall, where most of the papers do not have their data and code available. We also found some other reasons like the portability reason because of the platforms that the original authors did, they created their model, like the methods. They did not, like, we couldn't transfer them to a different platform, and that's because of the software used, which were the authors did not really specify the versions and all of that. So we found it difficult to transfer, to use a different platform. And then there were some of these papers that do not have detailed documentation about how to execute their code. They have a GitHub account, they have the code, they have the data, but no documentation on how to implement the methods that they propose. So we couldn't, there are some of them that falls in that category. And then the compatibility issue. So there are some of these papers that have the software they use have some dependencies. So probably some of those dependencies got outdated, but they did not specify the dependencies, like create a popular requirement or TST file. So we couldn't see the dependencies that those software actually have. And the last one here actually affected the one I showed, where the results we obtained was better than what was stated. That's so we tag that as the code durability. So what we observed here that the result we got for that method that was better could be as a result that the author updated the code and the methods after it was published. And since our method was majorly focusing on what was published, so it's possible that the author updated it, and that was why we got a better result. So, and we label such model a partially reproducible method. Okay, and then this is, so here we're actually focusing on the replicability based on a similar data set. So, and then we see the same methods we were examining this. So we saw that out of the 6 methods that were either executable or reproducible, only 2 of them were replicable. That's even not across all the IOUs, but across some IOUs. So only 2 of them. So that were replicable under some certain IOUs, but not even across all the IOUs. The where we have dash that where we couldn't replicate this TGRnet and rest of it because they were not, the method were not customizable to allow inference on a new data set. It was just, you can only reproduce it on the same data set that the authors used. So it was not customizable to allow a new data set. So this is the replicability, where we try to replicate the method on our own data set. And we found out that none of the methods that allow inference nor are reproducible was actually replicable on our own data set. So the R1, the R0, I've talked about that before. So the first slide, the first diagram is where we're comparing the original with the reproducibility on the same data set. And we saw that most of them were actually reproducible. That's what we indicate by this line. A perfect reproducible method, we have the data points lie on that straight line. And a method that is somewhat reproducible, we have it closer. So where we have this one above it is because that was the method that was better, where we obtain a better result. Now, and as you can see, the third diagram, which is on the new data set, that's what we call the R2 on our own data set. None of the methods even get close to what was obtaining the reproducibility result. Oh, sorry. Oh. Sorry, can you hear me? Okay.
Yeah, I can hear you.
Okay. All right. So this we found that none of the methods were replicable on our own data set, and that was why none of the points actually fall on that line. All right. So just to discuss the findings. So okay. So we realize one of the things we discover is that, I mean, replicability test or study is more challenging because it's not only depending on whether the method was executable, whether the code run without error, but it's also dependent on whether the method is configurable, can allow inference on a new, on a similar data set. So we saw that some of those methods were not configured in a way that you can test it on a similar data set. So, and also we saw that most of the methods that we found, we saw that they are data dependent, because if you look at this plot, this graph-based CSR only perform well on a data set. So in our own data set, like I said, we obtain it from 6 scientific domains, so which are what the domains listed here. The graph-based CSR did very well on a data set obtained from the material science, which we call math. However, very poorly on other data sets from other domains. And the Cascade TabNet actually obtained, I mean, fairly reasonable result across the domains. And that tallies with the result I shared on the reproducibility, because this same method will obtain a better result even than what was reported. So it shows that something is fishing there in terms of the data set. It could be that the data set used by this Cascade was more robust and diverse compared to other methods, because the result is a little bit consistent in both methods, like for both studies, reproducibility and replicability compared to other methods. So we also investigated that whether this reproducibility test or this study has anything to do with the ranking of these papers in the conferences where they were published. But we saw that the ranking has nothing to do with the reproducibility status of these papers, because some of the methods that had good ranking were not reproducible. Some that were reproducible had low ranking. So we saw that there was no connection between both. Well, the data set we use are actually as small in size, as you can see, but the way we selected them, in a way, we are trying to simulate an experiment that based on even that will work for larger ones. So one of the things we can do in the future is to try more samples. Like instead of focusing on 25 and narrow it down to 16, maybe we can try a larger size in the future. So that's our plan. So just to summarize what I've said so far, this study focuses on reproducibility and replicability, and we majorly consider 16 recently published papers based on that use deep learning on document images. So we not only check, inspect for code and data, but we directly reproduce these the papers based on the methods and the data set and the code that was published by the original authors. So we tested these methods on the same and similar benchmark data set, and also on a new data set that are more diverse and more scientific in nature. So, and then we realized that 12 out of those 16 papers were not fully reproducible. And only 2 of those papers were identified as being replicable based on a similar data set, and none of the papers were replicable with respect to our own data set, Gen TSR. I think so this work, I would like to thank my advisor, Dr. Wu, and the WSDL group as a whole. But this work was partially supported by the Institute of Museum and Library Services and the Defense Advanced Research Project Agency. So thank you. And I can take questions now. Thank you so much.
All right, thank you, Kitty. So I have one quick question. Have you guys thought about publishing a leaderboard or some other public place where you publish your findings about what is reproducible and what's not?
That's a good one. I've personally have not thought about that, but I think that's it's something that we can do. So yeah, it's a possibility. Yes, it is.
Yeah, I can take that question. That's a good question. So that's but for this particular task, I think there has been a leaderboard posted out there on Kaggle. However, a more meaningful thing that's actually in our plan is actually in our my NSF proposal is to build a database for build a reproducibility database for all kinds of AI tasks. Unfortunately, there are not many direct reproducibility experiment that has been conducted. So some papers have done reproducibility studies, but they hesitated to post the identity of these papers. But there has been the Kaggle machine learning reproducibility competition, which have been held for several years, and there are quite a bit of papers out there. And our goal is to build such a database and make it publicly available. So I don't know if you know that.
The idea being that replicability is to publicly reward the ones that take the time to ensure that, and essentially shame the other ones, right?
Well, we're not to shame the other ones.
Wow.
The people who don't like that.
Kind of, you know,
yeah.
It's shorthand.
But we want to encourage a more reproducible work, especially in AI. So from the research,
I mean, if you're not sharing your code or data, especially your code, right? I mean, what are you doing, right?
Right. Yeah.
Any other questions for Kenny? Okay, I think we're at our time. So again, everyone knows how to get in contact with us. So I hope you enjoyed the presentations. I'd like to thank all of our speakers, all of our attendees, all of our alumni that took the time to return with interesting questions, insights. We appreciate it. And we look forward to doing this again next year. Thanks, guys.
Thank you for organizing this. Bye.
Bye-bye.
Thank you. Bye.
Everyone, have a great day.